All right, in this video, we're going to review probability for the AP Statistics test. Probability is one of those topics that a lot of kids don't feel very comfortable with. There is a lot to it, but for the most part, I think the AP Stats test does keep it fairly simple. So I'm just going to try to focus on these 5 things. And there is going to be a separate video for the binomial model, which does incorporate a lot of probability as well. So number 1, we're going to talk about or versus and probability, which definitely will come up, multiple choice, maybe even on a free response. We're going to look at two-way table probability, which is actually the easiest type of probability. Most kids could solve that very easily with just some common sense. Then we're going to take a brief look at conditional probability with tree diagrams. Then we're going to talk about multiplication of independent events. And then finally, probability with normal model. So here we go. Let's dive right into it. So first, let's make sure you understand what probability is. Probability is the long-run relative frequency of an event. It's how often an event occurs in the long run after many, many, many trials. Remember, this is what the law of large numbers says. The true probability of any event will only reveal itself after a large number of trials. For example, everybody knows that the chance of flipping a coin and getting ahead is 50%. But what some people don't understand is what that 50% means. This means that in the long run, after many, many tosses, would we expect 50% to be heads. In the short run, anything is possible. If you toss the coin 10 times, you certainly might not get 50-50, right? You might not get 5 tails and 5 heads. I mean, that certainly is the most likely outcome, but that doesn't mean it will happen, because in only 10 tosses, you could get 6 heads, 7 heads, 1 head, 2 heads, 3 heads. I mean, who knows? So this goes back to the idea that bigger samples vary less. So if I were to toss a coin 1,000 times, only then, after many, many tosses, would I definitely expect to see something closer to 50-50. Now, am I still going to see 500 tails and 500 heads? Probably not, but it's much more likely in a larger sample than it is in a sample of only 10. So the true probability of an event is how often that event will reveal itself in the long run after many, many, many trials. Technically, many, many, many means infinite, because only then will you start to see that true 50% number pop up. All right, let's talk about 2 events, A and B. Now, the formula I have up here in green is the addition rule. This is probably one of the most important rules for you to remember, and it is on the AP Stats formula sheet when it comes to probability. The probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. Now, let's explain what we mean here. The probability of A or B means that if event A happens, we're happy. Or if event B happens, we're happy. But what a lot of kids misunderstand is that the probability of A or B also includes the probability of A and B. So the idea of A or B actually means A or B or even both. And that's what the formula tells us. So a lot of kids get confused by that because they see at the end of the formula that you actually subtract away the probability of A and B. Well, the reason why you're subtracting this away is so that that doesn't get counted twice. So the best way to explain this was with a Venn diagram, and I hope a teacher at some point showed you a Venn diagram. If I have 2 events, on the left A, on the right B, and in the middle is the overlap, that's the A and B. That's where both events are happening at the same time. So if I simply try to find A or B, I would take the whole A circle plus the whole B circle. But if I stop there, the problem is that overlap got counted twice. It got counted as part of the A circle, and it got counted as part of the B circle. So the reason why we have to subtract away A and B is to avoid it from being counted twice. So we're still including A and B in the OR formula, but we just don't want it to count twice. Because when you reference the probability of A, some of that could be only A, not B, and some of that could be A and B. Same thing can be said for the probability of B. Some of that could be B only, not A, but some of it could also be B and A. So again, now you can actually see that with the Venn diagram here. The overlap is the A and B, and if you just add up A and B, you're going to double count that, which is why you need to subtract it away. All right, so this brings up a good opportunity for me to mention mutually exclusive. Mutually exclusive means that A and B cannot happen at the same time. Now, if that's true, that would look like this. There's A, there's B, no overlap, they cannot happen at the same time. That means that the probability of A and B is a 0. So if you're mutually exclusive, and only if you're mutually exclusive, is the probability of A or B equal to the probability of A plus the probability of B. You don't have to worry about the overlap because there is none. So I guess you would just be subtracting a 0, which means nothing. Now, the next topic is A and B are independent events. If A and B are independent events, this means that the outcome of A does not impact the outcome of B. Now, if that is true, and only if that is true, that means that the probability of A and B is simply A times B. But this is a tricky formula because a lot of kids blindly use this. You can only use that formula if you know for a fact that A and B are independent of each other. And that's a little bit tricky to understand. So my recommendation is only multiply A times B. If you're thinking about and, only do so if you are directly told in the problem that the two events are independent of each other. Otherwise, you have to think conditionally, which we're going to get to in a little bit. Now, one other important statement to make, I've actually seen this pop up on the AP Stats test, is if two events are mutually exclusive, they cannot be independent. This is a one-way sentence. It doesn't work any other way around. It only works if it's worded exactly like this. If two events are mutually exclusive, they cannot be independent. And that makes sense to us because if you have two events that are mutually exclusive, like this picture shows right here, two events, A and B, that have no overlap, the moment that A occurs, B is impossible to occur because they cannot happen at the same time, which is what mutually exclusive means. So that means that the moment A occurs, it certainly affects the probability of B. An easy example I use in class is getting an A and getting a B on a test. You cannot get an A and a B on a test. You can only get one or the other. So the moment you get an A on a test, the probability of you getting a B drops to 0, which means A affected B. That is not independent. Remember, independent means they do not affect each other. So this is a pretty important statement to understand. If two events are mutually exclusive, they cannot be independent. Now, if two events are not mutually exclusive, that means they have overlap. Well, sometimes you're independent, sometimes you're not. It all depends. So that's why the only statement we know for a fact is that the two events are mutually exclusive. They cannot be independent. All right, let's put that formula to work. All right, the probability of event A is 0.24. 24% chance event A happens. And the probability of event B happens is 31%. What is the probability of A or B? All right, now we know the formula for A or B is the probability of A plus the probability of B minus the probability of A and B. All right, well, let's answer this question, but I actually cannot answer the question unless I'm told something. So the first question is, okay, let's find the answer to this if they're mutually exclusive. All right, if A and B are mutually exclusive, what does that tell me? Remember, if A and B are mutually exclusive, that means A and B is empty, impossible. They cannot occur at the same time. So if that's true, to find the probability of A or B, it's actually quite easy. I'm just going to take the probability of A, 0.24, plus the probability of B, 0.31, and I'm just going to add them together. What about the back part? Well, there is no back part because remember, the probability of A and B is 0. So I just add these together and I get 0.55. So this is a very common AP question. I see this a lot. They'll ask this type of scenario and they'll say, what happens if you're mutually exclusive? All you have to remember is that that back part, A and B, is 0. All right, what if they're independent? Okay, well, I'm trying to find the probability of A or B if they're independent. Well, I'm still going to use the formula. The probability of A is 0.24 plus the probability of B is 0.31 minus. Now, if you're independent, what do I know about the probability of A and B? Well, if you're independent, only then can I multiply. So the probability of A and B would be 0.24 times 0.31. Now, 0.24 times 0.31 is 0.0744. Okay, that means that the final answer for the probability of A or B is 0.24 plus 0.31 minus 0.0744, or 0.4756. So I hope that makes sense. Now, a couple kids say, well, what if I don't know you're independent? Well, to be honest, if you don't know you're independent, then you really can't answer this question. You do need to know one of these two things. If you're mutually exclusive, the A and B is 0, so all you got to do is add A and B. If you're independent, Well, then there you know for a fact that the probability of A and B is A times B. All right, let's move on. Now, let's talk about conditional probability here. This is where the outcome of one event does impact the outcome of a second event. Now, we write this with a line. So right here we say, what is the probability of A given, the back part is always the given that B has already occurred. Now, this is where we are not independent because this means that B affects A. So if the probability of A changes based on the fact that that B occurs, that is not independent. So the formula to find conditional probability is a really easy formula. On top, you find the probability of A and B. And on the bottom, you divide this by the probability of the condition B. So it's a really easy formula, also given to you on the AP Stats formula sheet. But I have to emphasize something. A lot of kids say, oh, okay, I know how to find the probability of A and B. Just multiply A times B, right? Only if you're independent. So please do not multiply the probability of A times B unless you know they're independent. That's only true if you're independent. So please keep that in mind. Otherwise, you have to hopefully be told or somehow find those probabilities. And we're going to explore that right now with this two-way table. I love seeing two-way tables on the AP Stats test, and so should you, because they're really easy to work with, especially when it comes to probability. So here's a two-way table that looked at 2,500 people, and it asked them their level of education, college grad, high school, but not all college graduate, and then not high school graduate. And then we asked, where do you get your news from? Newspaper, local TV, cable TV, the internet, or you don't get any news. All right, and then we have all of our numbers here in this two-way table. All right, first question is, what is the probability a college graduate is selected? All right, I want to choose a college graduate. That's the only thing mentioned in this problem. So how many college graduates are there? Well, if I look at the college graduate column, there are 693 college graduates divided by 2,500 total people to pick from. There's my answer. 693 divided by 2,500. And you get 0.2772. So that's a 27.72% chance a college graduate gets picked. Awesome. What is the probability that a college graduate is picked or someone who gets their news from the internet? Okay, I see that word or, so I got to use that or formula, right? The probability of A or B. College graduate is A, or getting your news from the internet is B. All right, so I'm going to follow the formula. Okay. I'm going to find the probability of college grad. All right, the probability a college graduate is picked, easy. We just got done finding that, 693 out of 2,500. Or I'm going to add the probability that I get my news from the internet. Okay, the probability I get my news from the internet is 687 people get their news from the internet divided by 2,500. But now I have to subtract away the and. Now, don't use any fancy formula to find and, just look at the table. How many people are both college graduates and get their news from the internet? That would be these 245 people right here. Now, I'm going to subtract away the and. Those are the people that are both college graduates and get their news from the internet. Now, I want to emphasize this again. I'm not getting rid of those people, but if you think about it, those 245 people were counted among the 693 college graduates, but those 245 people were also counted among the 687 internet news source people. Well, those 245 people definitely deserve to be counted, but not twice. That's why I'm subtracting them away. So 693 plus 687. 693, 687, subtract away the 245, I get 1135 out of 2,500. Remember, I got a common denominator there, so I'm just adding the numerators. Divide by 2,500, I get 0.454. So again, all you got to do is use a little bit of common sense there and think your way through it. All right, next question. What is the probability somebody who gets their news from the internet and is a college graduate is picked? So what is the probability that somebody gets their news from the internet and they're a college graduate? Oh, we already talked about that. That is a very specific 245 people. That's it. Easy. We already know that. It said and, don't multiply, right? I don't need to multiply. I got this table in front of me that shows me everything I need. I'm looking at this table and I clearly see 245 people that get their news from the internet and are college grads. That's it, 245 out of 2,500. Don't make it harder than it is, 0.098. All right, next question. What is the probability that What is the probability that a college grad is picked given he or she gets their news from the internet? All right, now I see that word given. That's conditional because I'm told that they give their news from the internet. That's a given. So I'm trying to find the probability. I'm trying to find the probability that they are a college graduate. But I'm given that they get their news from the internet. See, this is using that conditional formula. I know something about this person prior to picking them. I know that they get their news from the internet. Now, I actually don't need a fancy formula for this. I just need a little bit of common sense. The fact that I'm given that they get their news from the internet means I'm only allowed to look at the 687 people who get their news from the internet. That goes on the denominator. Because, again, if they're given that they get from the news from the internet, everybody else I need to ignore because they don't get their news from the internet. I'm only allowed to focus on the 687 people who get their news from the internet. Now, of those people, 245 of them are college graduates. So again, this is using the formula. On top goes both, college graduate and get their news from the internet. That's the 245 people we've already mentioned a couple times now. The denominator is just getting your news from the internet. And that is the 687 people that get their news from the internet. And that is conditional probability. So conditional probability, your denominator changes because of that condition. So now 245 out of 687 is 0.3566. All right, final question. Is being a college grad independent of getting news from the internet? All right, this is actually a really easy question to answer now. Okay, the probability of A given B, right? That's conditional probability. This means that there's an event B that is happening prior to event A. Now, if this equals the probability of A, what this tells me is that I'm independent because this tells me that B did not impact A. On the right side, all I care about is A. And if that is equal to caring about A after B has occurred, and if I could show that those two numbers are equal, then what that means is that what that means is that A and B are truly independent of each other, because this means that B did not impact A. Let me briefly go over this one more time. Let's think about this real quick. If you're independent, what do we know about A and B? We know that the probability of A times the probability of B is A and B, only if you're independent. Well, if that's true in this formula, the probabilities of B are going to cancel, and we get the probability of A given B equals the probability of A, thus verifying that only if you're independent is the probability of A equal to the probability of A given B. So if I want to show that being a college graduate is independent of getting news from the internet, I need to show that the probability of being a college graduate, given I get my news from the internet, is exactly the same as the probability of getting a college graduate. See, what I want to show you is that getting your news from the internet doesn't affect being a college graduate. Well, let's find out. All right, what's the probability you're a college graduate? That was actually the very first question we answered. It was all the way back up here. Being a college graduate, 693 college graduates out of 2,500, 0.2772. So I'm just going to fill that in right there, 0.2772. That means there's a 27% chance I get somebody who's a college graduate. Now, what's the probability I get a college graduate given you get your news from the internet? Well, I already found that as well. That was 0.3566. Again, the denominator was getting your news from the internet. 687 people get their news from the internet. The numerator is both news from the internet and college grad, 245. Now, these two numbers are not equal, which means we are not independent. And this actually makes sense. There's a 27% chance that somebody is a college graduate, However, if you get your news from the internet, the chance of you being a college graduate goes up to about 36%. This means that getting your news from the internet does impact, or there is an association with you being a college graduate. You are more likely to be a college graduate if you get your news from the internet. So this shows that the two events are not independent. If they would have been equal, it would show that they are independent. I have seen questions like this based on a two-way table come up quite frequently on the AP Stats exam, so please be ready for them. All right, now let's talk about conditional probability again, but this time through a tree diagram. This is another very common AP Stats type question. Studies show that 2% of dogs get heartworm. A new test is used to help diagnose dogs with heartworm. If a dog has heartworm, it will give a positive test result 95% of the time. See, that if there is given, right? That's a big conditional thing. On the condition that a dog has heartworm, will they get a positive test result 95% of the time. If a dog does not have heartworm, again, conditional, if the dog does not have heartworm, it will give a negative result 85% of the time. So what's best is to create a little tree diagram here. So let's have a little dog here, right? Little dog here, and there's his tail. Okay. Now, there is a 2% chance that this dog has heartworm. I'm sorry, that's unfortunate. 98% chance they don't. I just use a little bit of common sense there. Hope you're okay with that. Now, the first statement said if you have heartworm, so I'm going to follow the heartworm branch. If you have heartworm, there is a 95% chance of a positive test result, which means there's a 5% chance of a negative test result. Now that would obviously be bad. A negative test result would tell you that your dog does not have heartworm when they really do. Now, the other statement was if a dog does not have heartworm, he will give a negative result 85% of the time. So if your dog does not have heartworm, so I'm following the not heartworm, there is an 85% chance of a negative test result, which means there's a 15% chance of a positive test result. Now that would also be bad because that means you're saying your dog has heartworm, but they really don't. So what we see here is we see what's called a false positive. It's a positive that's wrong. And we see a false negative. That's a negative that's wrong. All right, now what can I ask you now that I have this beautiful tree diagram drawn up? Well, one thing I could ask you is, say, what's the probability a dog has a positive test result? Well, there's two ways you can have a positive test result. Heartworm and positive, no heartworm and positive. Okay, all I got to do is multiply heartworm and positive test result, or no heartworm and positive test result. Those are the two branches that lead to a positive test result. And again, I'm allowed to multiply because it's conditional. This 95% was on the condition that you had heartworm, 2% chance. This 15% was on the condition that you did not have heartworm, 98% chance. So all I got to do is multiply that, 0.02 times 0.95 plus 0.98 times 0.15, and I get 0.166. So that is the probability that a dog has a positive test result. All right, another question that's very common is this. Given a positive result, what is the probability the dog has heartworm? Now, this is an important question because notice you could get a positive result and not have heartworm, or you could get a positive result and have heartworm. So we're saying, all right, givens, this is conditional. Given that you have a positive result, what's the probability that you have heartworm? So I'm trying to find the probability that a dog has heartworm given a positive test result. All right, well, let's use the formula for conditional probability. On top goes both heartworm and positive result. Heartworm, 0.02, and a positive result. Based on having that heartworm, 0.02 times 0.95, that's the top. On the bottom goes only the condition, a positive test result. Well, we already calculated that. A positive test result is 0.166. Now, remember, that was two things because there's two ways you can get a positive test result. Heartworm and positive, no heartworm and positive. So those are the two things that would go on the bottom, but we already calculated that. So now all I got to do is a little bit of math here. 0.02 times 0.95 divided by the 0.166, and I get 0.1145. And if you want to confirm on your calculator, you can. So that means that if I get a positive test result for my dog, there's only about 11% chance that my dog actually has heartworm. Now, a lot of people say, well, wait a minute. It's a positive test result. Doesn't that mean they have heartworm? Yes, but remember, very few dogs, most dogs don't have heartworm, which is why that fake positive is probably what's happening here. Now, obviously, there's still 11% chance your dog really has heartworm, but the point is, since heartworm is a pretty rare thing, most dogs don't have it anyway. So if you get that positive result, don't panic. Your dog might not have heartworm. So there's 11.45% chance that you actually have heartworm if you get that positive test result. But this is a classic tree diagram problem where you see these if statements. So please make sure you understand that that leads to a tree diagram. Make sure you know how to draw one and use one to help you out. All right, next up here, I want to talk about multiplying for multiple events. Now, the point I want to make here is that when you're talking about multiple things happening, okay, now I'm not talking about both. I'm not talking about both here. I don't mean that you are both a boy and you have blonde hair. Okay, I'm talking about doing something and then something else and then something else and then something else. So I'm doing things multiple times, right? Multiple events. You just multiply, but all you have to do is make sure you think about conditional probability. As long as you think about it, there's no special formula here other than to multiply. So anytime you want to find probability of one thing happening after another, just multiply. As long as you consider if the outcome of the first event might have changed the outcome of the second event. And we're going to see that right here. All right, so a room has 4 boys and 3 girls. So 7 students in a room, 4 boys, 3 girls. What is the probability that 4 kids are picked and they're all boys? So all I got to do is walk through this. All right, I need 4 kids to be picked. What's the probability that the first one is a boy? Well, there's 4 boys out of 7 kids to pick from. But I now need another boy. See, I'm going to multiply because I need another boy. Well, 1 boy's already been picked, so there's only 3 boys left, but 1 kid has already been picked, so there's only 6 kids left. All I did was use my brain to think conditionally because the outcome of this first boy affected the outcome of the second boy. Now I need a third boy. Well, I've already picked 2, so there's only 2 left. And there's only 5 kids left. You get the idea. And then now I need a 4th boy. Well, there's only 1 boy left out of 4 kids remaining in the room, and now I'm done. All I got to do is multiply that out. Now, you can multiply that out on your own. It's not that hard to do on a calculator to get your final answer. All right, I'm going to move on to the next question here. The teacher wants to select a girl. Build a probability model for how many kids have to be picked to get a girl. All right, so I want to build a probability model for how many kids can be picked to get a girl. So the moment I get a girl, I'm done. All right, so X is going to be my random variable for how many kids need to be picked. All right, let's kind of just walk through this. A probability model has the probability of each outcome beneath it. All right, so could I get a girl with only picking 1 student? Absolutely. What has to happen to get a girl with 1 student? Well, I need to pick a girl. There's 3 girls to pick from out of 7. Boom, I'm done. Or could it take 2 kids to get a girl? Well, for it to take 2 kids to get a girl, that means that first one had to be a boy. So that would be 4 over 7 to get that boy. And then I have 3 girls to pick from out of 6 kids remaining to get that girl on the second kid. So again, to have the second kid be a girl, that means the first one was a boy, and then the second one was a girl. Could it take 3 kids? Absolutely. That would be boy, and then a girl. So 4 out of 7 for that first boy, 3 out of 6 for that second boy, and then finally, on that third kid, I get the girl, 3 girls out of 5 kids remaining. Hopefully you're getting the point here. Could it take 4 kids to get a boy? Or to get a girl, sorry. 4 kids, yeah. That would be boy, 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 and then I get that girl. All right, so once again, 4 out of 7 for that first boy. 3 out of 6 for that second boy. 2 out of 5 for that third boy. And then finally, on the 4th kid, I get the girl, and there's 3 out of 4 kids that are girls left in the room. All right, could it go to a fifth kid? Absolutely. That would be boy, 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 which at that point I've exhausted all of my boys because I only had 4 of them, and then I must get that girl. So that's 4 out of 7 for the first boy, 3 out of 6 for the second boy, 2 out of 5 for the third boy, 1 out of 4 for the last boy, and then there's no boys left, which means I got a 3 out of 3 chance, which is a 100% chance to get a girl. Now that's it. I will never have to go to 6 kids because that's impossible, right? Why would I need to go to 6 kids? There's only 4 boys. So if I pick all 4 boys, I'm guaranteed 100% chance, 3 out of 3, to get a girl in that 5th boy. So you guys can multiply those out to actually get the probabilities, but there are the different outcomes for I need to get a girl. I could get a girl in the very first kid, second kid, third kid, fourth kid, or I might have to wait all the way to that 5th kid. And again, that's how you build a probability model. And all I had to do was think conditionally. I didn't need any special formulas. I just had to use my brain. Now, there are some events that are independent, meaning that they don't affect each other. For example, if you're if you're going to throw a die, right? The probability of any outcome on a die is 1/6. Well, the outcome for one die has no impact on another die. So if I said, what's the probability you get 4 5s in a row? So 4 5s in a row. Okay, well, I got 1/6 chance to get a 5. I got a 1/6 chance to get another 5. I got a 1/6 chance to get another 5, and I got a 1/6 chance to get another 5. So there's my 4 5s in a row. And I didn't have to change the probability because they're independent. That die doesn't lose a 5 after it rolls one. It's not like a classroom where you're picking kids. So those are independent. So here's my 5, here's another 5, here's another 5, here's another 5. There's my 4 straight 5s, 1/6 chance for each. Multiply together, you got your answer. So the point is, when you're doing multiple things, always multiply. Just be careful to think conditionally if need be. All right, the last thing I want to leave you with here is that many questions that ask for a probability directly relate to the normal model. Recall the problem must say the normal model, or that the normal distribution is being used, and then you will need a mean and a standard deviation. Then all you got to do is use normal CDF on your calculator. Never be afraid of a problem relating to the normal model that asks for probability, because normal CDF could be your best friend. All you got to know is to use z-scores. Now, if the problem deals with a sample size of n, don't forget that the standard deviation for a sample mean or a sample proportion will change based on the appropriate formula. Please check out the videos for normal models and the video for sampling distributions for more examples of these types of problems. But the point I'm trying to make is that the probability can be used in these settings as well, but those are pretty easy, and I've actually already covered them in those other videos, so check them out, please. Also be aware that there is binomial probability, right? There's going to be a separate video for that as well. So if you're interested in binomial probability, which is really great and very common AP questions as well, please check out that video for that. All right, that's it, guys.